Good. I think it's good. We're not sure it's good.
I think I got the second one, no problem, in the first one.
So combined materials gotta work together. That's the key. So if they're not working together, it's not a combined material problem. Right? It's just like the ones we did before where like one piece is stuck to the other piece, they can expand differently, right? So if they are conformed and working together, it's a combined material problem, like this piece of wood. So this is a cross section, meaning that we are looking straight down the post, right? Looking straight down the post. And there's steel plates here and steel plates here. It says it's a short post. And that's actually important. You don't know that yet, but long posts we have to do a different analysis on. We have to do buckling and some other things. A short post, we just do compression. Just compression. So the plate's 150 by 10, the wood is 150 by 150. They want us to find the load, how much it can carry. So kind of the three formulas we have the relationship between the two stresses and then the modular ratio. And that's EA over EB, or the stronger modulus of elasticity over the weaker modulus of elasticity. So we have that relationship. If we want to know, like, if the question was, hey, what's the stress in the material, then we would be thinking more about stresses than this load thing. We have two load equations, areas of each and then stresses of each. So if for some reason you knew the stress levels, right, then you could work through that. And then this one gives us the load based on the weaker stress, maximizing the weaker stress. So this is the one we want to use because we can look up the stress for wood, right? The compressive stress for wood is 7.24. We do need the modular ratio, so let's get that. N equals EA over EB. EA of steel is, anyone have that? How much?
29.
29 in the metric system.
207.
Yeah, 207. Of course, my book has 200.
Or yeah,
So-
I've got 200. I just saw.
I'm sorry about that. I don't know why it's changed, but the current book has 200. Huh?
That much.
Yeah, that's a lot. I agree.
Yeah.
Anyway, so leave it, don't erase it. Just put a note on there. 200 times 10 to the third 3. So I write that E to the 3, and that's not this E, right? That's exponential. That's what that E is. Megapascals. And then what's the other material? Doug Fir. What do we get for that? 12. Yep.
I was curious with this. It's perpendicular. Or excuse me, it's not parallel.
Yeah, so we're looking straight down it. So the
The
load,
grade is
yeah,
that way. Okay,
yeah.
cool.
So what do we get for the N value? 16.67.
16.67.
Everyone see where I'm getting that? Good. So that's this modular ratio. So now we should be able to take P, and what do we put in here? Because areas we can find. What's this? It's the stress of wood, and you put the limit in. So you send the weaker material to the limit, right? Send the weaker material to the limit. It's like if you had a bunch of people holding onto hands and you're going to pull them apart, and in the middle there's a kid. Well, clearly, like, whatever the kid can hold is what the whole chain can hold. So same thing. We put in the limit for the weaker material. The limit for the wood is 7.24 megapascals. So 7.24 megapascals. And then it is modular ratio 16.67, area of the steel. So that's 150 times 10, which is 1500 times 2. There's 2 of them.
Oh,
Right? So 3000. And what's the units of that? Millimeters squared. So we have to be careful with units again. And then area of the wood is 150 by 150. I just want a number, so I'm going to calculate that.
22 but
22500. All right, so we have a problem because a megapascal is what? What's a Pascal? Yeah, so I'm gonna get rid of that unit. I'm gonna rewrite it in just so I can see it. P equals 7.24 E to the 6 Newton per meter squared. That's mega, E to the 6, exponential to the 6, right? But now I have meters squared and millimeters squared. So I have a problem. There's 1,000 millimeters per meter, correct? 1,000 millimeters per meter. But I need square, so I have to square everything. So to get those units worked out, you have to divide by 1,000 squared. Because we have millimeters squared in here. In the future, you might want to just put meters in for this area, and then you solve your problem. But if you just put the millimeters in, you have to deal with that. Okay, let's see if I can calculate this number. Anyone get 524? Yeah. What's your number though? Is it
3.18, either the 6,
2.18,
3.18.
3.18?
If I put in the 200, it's 3.07.
All right, let me calculate again.
what was your 524?
Yeah, that's what I got. E to the 3.
Yeah,
So I'm gonna do it again. 7.24 E to the 6. Problem. Yeah, I got it again. So I'm getting 524.97 kilonewtons. See what the book got. Anybody else get that?
yeah, I got it. 524, but I got it.
They get 538.
524. That's
I'm guessing it's rounding because they got 3,000. At 124, 22 fives, right? Times 10 to the 3 and 724. Yeah. So where are you different, Aiden?
I don't know.
Yeah.
All my units cancel. I didn't do it how you did it for the millimeters. I converted it straight to meters.
Yeah, that should work. Like, that's just the conversion of millimeters to meters.
What'd you get again?
I got 3.18 e to the 6.
I'm so far off. Right, no.
Well, let me see what I get when I do it this way. So I'm gonna take the modular ratio. Yeah, that should not matter. 7.24.
In the modulus ratio.
Yeah.
That's unitless.
Yeah. Oh, that could be the problem. Oh, that's why the solution's wrong. They use different E values because the book E value changed also. So
It's not
Yeah.
well.
that would be the problem because their modular ratio is like less. It's 15 something. So let me I'll put in meters and do it that way. 16.67 in there. Yeah, it's just gonna change the decimal position is all it's gonna do. It's all right, I'm gonna do it. Yeah, I get the same number, 524.97. Don't know. I'm happy with my number, so there you go.
I thought I was happy to find number too.
Yeah. What's different?
I don't know.
Are you running this formula?
Yeah. I'm gonna get.
What do you get for N? You get 16.67?
Yeah.
What do you get for the area of the steel?
Uh.
0.03?
Yeah.
15 times 0.1.
How much?
0.15 meters times 0.1 meters.
What is that? Should be like,
0.015 meters.
yeah. So
I got
times
it.
2? Did you do 2 plates? You got what?
I ran that equation in units. That's. But we're.
And then, so what are you getting for the area of the wood?
0.0225 meters.
Yeah, it's the same number.
I'm literally getting the exact same stuff you are.
And then you're using 7.24 e to the 6?
Yeah.
Wow, this is not that complicated. If I'm mucking it up, it's not that complicated. Yeah, I don't know. Area of the steel. Is 003. Area of the wood. Is 0.0225. N is 16.67 and this is 7.24 e to the 6.
Yeah, when I read it as you have it, it goes even higher. When I write it that way, I have 8.14 to the 9.
Wow, I get it again. So I don't know what you're doing. I want to know though, because I want to solve that problem, but
I'll look at it.
all right. Second one is our wire. We got a copper coated wire, a steel core, and a load of 8,000 pounds. So, and they want to know what's the stress in the steel, what's the stress in the copper. Which is material A? Is it going to be the copper or the steel? Steel. The highest modulus. It's definitely the steel. So it's going to be literally the 29,000 over the 15,000 and is going to equal just under 2.
Yeah,
1.933. All right. So we want to know, like, what's the stress in both of these? And potentially neither one is to the limit. So we don't use this formula because this is the formula we want to use for the limit. How are we going to do this one?
You said P to 8,000.
Yeah, so we can set P to 8,000, right? But these are going to be unknowns. And this is going to be unknown. So
But we can just find that by running another equation, right? That's what I did.
you can find this, right?
Yeah.
Yeah, exactly. That will be your only unknown. Because we know n, correct?
Yep.
We know area of both, so we can calc this. So in this case, we don't set it to the limit, we actually calc it. Perfect. So I'm going to write it here, 8,000 pounds equals the stress in the copper, because it's the weaker material. The modular ratio 1.933 times the area of the steel, which is going to be pi d, which is 0.5 squared over 4, plus the area of the copper.
And you
So-
subtract out those steel.
That's the way I do it, because I do a big diameter and then subtract this thing out, right? So it'd be pi, the large D is 5H, which is 0.6, no, yeah, 0.625. Minus the core. Looks something like that. So this is the area of the copper. This is the area of the steel. This is N. And then we have a little algebra to do. It's 8,000 and we divide by this entire number. So some calculator gymnastics. I get 16,326, so. So everything's in inches and we have pounds, so it's gonna be PSI. This is the copper. And I think the yield for copper is like 40,000. So it's good. Anyone else get that number? Aiden, did you get that number?
No,
Yeah, I got a little. Got 17,962.
I got 19,517.
Wow. But you have all the same numbers as
I
me?
got the same numbers.
All right, so let's break it into pieces again. What's the area of the steel?
I,
I mean, what's the number?
0.1965 inches squared.
Yep, that's what I get. I'm gonna write it right below it, 0.1963. And then what do we get for the area of the copper?
0.045.
Point 11045. And then when we take this times the n, so inside this bracket will be the next thing we get. 96, there it is. 1.933. Everyone has 1.933 for n.
yeah,
Okay. So inside the bracket, I get 0.4899. When I combine all of this. Anybody else get that?
what did you get for inside the bracket?
I got 0.48999.
I get 0.593.
What do you get?
I did it a different way.
Oh, no, you had all the numbers. You had all the numbers. I'm just trying to, I did a different way too. I'm just trying to break it into pieces.
I have all the same numbers.
Yeah, so if you have this number and this number and that number, we should have that number.
Let's go to 8,000.
And this just divides into the 8,000.
What did you get for steel?
0.4899 was what you got for inside the bracket.
Yeah, 0.4899,
Yeah, that's what
What do you get for the area of steel and copper?
0.1963.
Okay, yeah. I got that. And what was the other one?
Area of the copper,
Yeah,
0.11045.
yeah, I get that too.
And you have 1933,
Yeah,
and you're multiplying these two together.
yeah.
And then adding this.
So, oh no, I'm getting the opposite way.
What's
Is it not the,
this?
it's the strong material, which is steel.
Steel.
Steel's the inside one, okay.
Yep,
Yeah, I flipped those two.
perfect. Now we just gotta figure out what Brandon did.
okay, so I wasn't here, so I had to like learn elsewhere. But what's the O for the C right there, what's that?
Copper.
No, what's the symbol?
Oh,
Gamma.
gamma? No,
What is it,
sigma.
Okay, sigma.
Yeah,
So sigma of steel over the elastic modulus of steel equals Is that an equation? Cause I did it in a completely different one, but I got, my answers were close.
So. So you're saying sigma of steel
Over
over
the elastics, modulus, yep, over E.
Of what?
Equals.
Of what?
Steel
steel.
equals, same thing, but copper. Yes. Yeah, we.
Yeah, I think that's,
Okay, so I
let
use
me just
that.
see if there's a phase. Hang on. I just wanna make sure. Yeah, so they put it in this form.
Okay. Oh, that's why I confronted the push.
Yeah,
Okay, cool. So I did, what I did is, 8,000 equals the area of steel times steel plus, right?
whoa. Are you down here now?
Yes.
Okay,
Okay, so 8,000 equals area of steel times sigma of steel plus area of copper times sigma of copper. And I used the other equation and I solved for the sigma of steel, so I got the sigma of steel equals 29 KSI, 29,000 KSI over 17,000 KSI times the sigma of copper. And then I just put that back into the equation and solved.
so you
that.
did simultaneous equations.
Yeah. Yeah.
I-
I got, yeah,
I would think that would work. If there was no mistaken,
I might have made a mistake. But I got close though.
making it hard.
Yeah.
Yeah, I'll look at it and see,
Okay.
like, that could work, I would think. Cause you didn't put in a limit, you left those both unknown,
I didn't use N.
but you used e's, so you did use n.
Right.
Yeah, so you can, I mean, n is just ea over eb.
Right.
And that was in your initial equation,
Yeah.
this thing, right? So. Should work,
Okay.
n's in there. Cool,
And to get the.
to get the other one,
You just multiply it by N.
yeah, you just go back to this formula, which is the stress of the stronger material equals n times the stress of the weaker material. So now that we have the stress of the weaker material, we just take n times it to get the stress in steel. So that would be what? I'll just write 1.933, I'll write it out. Times 16,326 equals. What'd you get?
31,559.2. You got 3640.
Yeah, you're not far off, that's for sure. Except for the yield of steel is 36, so yours failed and ours didn't, so. Yeah. Very good. Most of our power distribution grid in the United States is this. We have steel cores. So. They carry a bunch of load too. Some of those spans are crazy big. Questions? Good job. Fighting your way through it. All right, let's turn those in. Get them out of your hair. Well, let's talk about stress concentrations. We just keep moving on.
I'm a little bit confused what we did with the stress of steel, like, we times N by,
So one of the formulas is the stress in A
oh,
equals N times the stress in B, the weaker.
yeah, stress would be times N.
Yeah.
I see.
So once you find the weaker stress, which we did, right? Then you just take it times N to get the stress in the other material.
Okay.
Yeah,
Thank you.
and the yield for steel is still 6, so it's still good. What's interesting is the copper stress is much lower, that's the weaker material. And the steel stress is higher, but that's because of the area difference. It's quite a bit of area difference in that, so. All right, stress concentrations. This is pretty easy. Pretty straightforward, can't miss a step kind of thing. When we change the cross section of something that is loaded. So change the cross section means we poke a hole in it, or we put notches in it, or we just reduce the area, right? The bar of steel is traveling along, and then all of a sudden the bar of steel gets thinner for some reason. So if you look at most of the heavy haul trailers that are out on the roadway, like next time you're in a traffic jam next to a semi truck, just take a look at the frame that's carrying that big trailer. It'll have a bunch of holes in it, like where they had to send plumbing through or something, or the section will taper. It'll change its cross section, right? So that creates what we call stress risers or stress concentrations.
Will thermal affect that?
Thermal just takes the whole thing and can exaggerate these stresses. But like in a trailer, it's free to expand. It's on wheels on both ends, so it can heat up and get longer. Some of those trailers will get ½ inch longer in the super hot weather, or ½ inch shorter in very cold temperatures. So, yeah, no thermal stresses in those things because they're free to expand. So this little diagram is actually, these are stresses. So stress max is here next to the hole. So average stress, that's what we've been calculating back here in the section away from the hole. That's what we calculate when we calculate P over A. Some of you were thinking about just using this reduced area, and that's called the area net, the leftover area, and that will create a higher stress. So if we had the stress here, and then we calculated the stress here with this area gone, the stress would be higher because there's less material to carry the same load, right? That makes sense? But it even goes higher than that. It spikes near a hole. And depending on how big the hole is, very small holes can create very high stress risers. The larger holes can actually create less because they have more kind of concavity to them than a small hole. So it's not always, small hole, big hole, how do I know, right? So there's got to be a way that we calculate these stress risers. In this class, in this book, you can only do 3 geometries. You can do a hole, you can do notches, or you can do, I think they call these semicircular grooves or something, but it's a reduction in area. Just those 3, right? Out in the real world, you can do pretty much any geometry. You just have to look up the graph because there's a graph for each kind of dimensional change. So for a hole, there's this graph. For semicircular grooves, there's this graph. And on the next page, there is the fillets or the reduction in area, this graph. So different graph for different geometries, trying to figure out what this stress riser is, okay? These graphs give it to us. So where we normally calculate stress as P over A, right? Stress is P over A. When we're doing concentrations, it's K times P over A net. So we do use that reduced area. So that's the first thing. You have to figure out what A net is, the reduction in the area. And then you have to figure out the K factor. Okay? Reduction in area is pretty easy. They do give you like ways to calculate it, but it's pretty simple to calculate. Like, if this was a 4-inch by a 1/4 inch, right? The load out here is going to be, and I'll put what, I don't know, 3,000 pounds on it. It's gonna, the stress out here is gonna be P over A, 4 times the 1/4 inch. Right? Away from the change. The stress here is gonna be P over A net, which is this area reduced, and we would have to know this whole size. I don't know, I'll say a 1/2 inch. So I'll draw this out. We're gonna do 4 inch by a 1/4 inch and a 1/2 inch hole. So we got a pretty big plate. 4 inch. What'd I say, 3,000 pounds?
Yeah.
And then a 1/2 inch hole. And we're a 1/4 inch thick. Everyone okay with that? Just made it up. What do you think? 1/4 inch by 4 inch should be able to carry 3,000 pounds, right? I think so. We'll call it steel, mild steel, 836. I left my coffee cup in the bathroom, really disturbed about it. Then somebody went in there and they were in the stall for like 40 minutes. I'm like, oh my God. I kept going back to get it. And this person's like camping in the bathroom. I'm like, killing me, man. So I keep thinking about my coffee cup, hanging out with this.
It's gone.
This dude. Ah, so sad if it's gone. That's my favorite. All right, so let's calculate our normal stress first, just our normal tensile stress. So that's out here somewhere, away from the hole. So we all know what that is. It's P over A, 3,000 over 0.25 inches times 4 inches. Right? This is our average stress. What do we get?
Oh.
Yeah, interesting.
Yeah.
It's kind of bad luck, but whatever. 3,000 PSI. What's our factor of safety? It's 836 steel. Oh. 36,000 is the yield. What's our factor of safety? 12. 12 times 3 is 36, exactly. Factor of safety of 12. Good so far? That's our normal average stress that we've been calculating for 6 weeks. All right, now let's get what I call the stress, the tensile stress net. So tensile stress net is going to be P over area net, which means that's here. That's just the reduction in area, right? So that's going to be 3,000. And instead of the 0.25 times 4, we take this 1/2 inch away. It's 0.25 times 3.5. Right? Because it's a 1/2 inch diameter. What's our new stress?
0.28.
Yep.
800.
Wow. Dude, you need to trade in that calculator.
Oh, it's that added and divided.
How
Alright, instead of multiplying.
many classes do you have?
6.
Okay, this is strength of materials. All right, this is strength of materials. Okay, poor guy. It's memorable though, Aiden, I gotta say. In my 30 years, I'm not sure I've had someone go for that, so. Everyone good with this so far? All right, so that is I mean, that's one way to calculate, oh, there's additional stress for sure, because there's less material, right? But now we need the final one, which would be the stress concentration, which is going to be K, P over area net. So we already have the P over area net, that's that. We just need to figure out this K thing. So the K thing is a graph, and it's basically the R to D ratio, R to D ratio down here, and then you read the K factor off the graph. So we don't make the graph, we use the graph to read the K factor. So we have to be able to calculate this R to D. R stands for radius. And it gives you like the little d. So this is a little d, not a big D. It's the little d, which is the distance of the material that's left. Right? Big D is the 4 inches, little d, and they call it half little d because it's half right there and half right there. I just call it the leftover material, the distance, right? So we have 4 inches and we're taking away a half. So our D is what?
1.7. Half will be
Half of it is, what's the full D? Because we want R to D.
5.
3.5, yeah. So just think about like, oh, it's the distance of the material that's left over, right? And then this is the radius, R to D. So for us, R to D is, radius is 0.25 inches, right? It's half of my half. And then divided by the distance, which is 3.5. So this is 1/2 D, and this is 1/2 D. I don't love the way they put that, but you can kind of get a grasp on it. Does that make sense? All right, what's our R to D? 1.428. I want to say 8, and what'd you get, but I'm not gonna.
Because I did not get that.
Seriously?
Yeah. I got 0.07.
I got 0.07. Well, you're right this time. Aaron's off his rocker.
Yeah, I got, okay, that's what I got.
Yeah, huh?
Oh, I did 0.5.
0.071. All right, let's read this graph. Because that's the number we need, 0.071. We got to go to the correct graph, and that's the one that has the hole, not the semicircular groove one, right? So you got to go to the correct graph. And you got to find 0.071. Well, I made this pretty hard. 0.071. So there's 0.1. So we're before 0.1, correct? Yeah, 0.0. So what's this? 0.05. Yeah. Again, it's a graph. We're not all going to read this exactly the same. I get that. But I'd say it's right in there. That's about half the distance. Right? So you come up. I'm going to put a little line. Then I'm going to read the graph over to there. So this is 2.6. This is 2.7. This is 2.8. 2.7. Yeah, again, it's a graph, right? So I say it's 2.7. This would be 7.5. I say 7.7. Good. But again, it's a graph. We're not all going to get the same. 2.77 for the K factor, and that's unitless. And it's basically a multiplier to this. It's a big multiplier. It's doubling your area net stress, right? Yeah, it's a lot. So 34.28.
On the stress of T, what's under that? Okay,
Here,
what's that, yeah.
concentration.
Okay.
Yeah, you can put anything you want in there. I should have wrote the whole thing out probably.
You say K is unitless?
K is unitless, yep. So 3428.57 enter 2.77 times. That gives us 9,497.
So there's no like formula for that graph, it's just like. Refer to the graph and. That's so weird.
So there is not, but there is online. So you can go online and find the stress concentration data. And it's pretty cool because then you can just input your number, your R to D ratio, and it'll pump out the exact number. But the thing is, I never want to say it's not that important that we're that accurate, but what we're checking is that we are magnitudes under the yield stress, right? 9,000 is still a factor of safety of what? To 36,000. It's like 6, right? It's a little less than 6, but the factor of safety is still very large. We're nowhere near the yield. So if we're off this little bit and the K factor, it's fine. Now, if this ended up to be like 35,800, I'd be like, oh shit, we're right at it, right? That's a problem. And maybe I want to get more specific with that graph. Yeah.
Are they concentrated? The P, do you use you don't use the net P? Do you, the 3,000?
There's only one P.
Just
The
3,000?
load never changes. Yeah, so it's 3,000 here, 3,000 here, and it's 3,000.
Okay.
Yeah, load never changes. So this was the average. This was the stress net, just in the reduction of area. And then this is the concentration, the spike. So in this graph, this stress graph, that's our spike right there. This is like area net was in here somewhere, and then average is out here somewhere, right?
That's just for like a plate, correct? That's not a cylindrical object?
No, it's not a cylindrical object. This is like a flat bar. Yeah.
So if it was cylindrical, would it be a totally different?
Oh God, yeah. Yeah, it's 3-dimensional,
Do quarters
finite element analysis type problem. Yeah.
create a lot more stress?
Sharp edges?
Yeah.
Absolutely. Yep. We try to fill at everything that's going to be loaded, rounded off. Yep.
I have.
And so it's the same process, same exact process for this kind of a reduction or this kind of a reduction. Right? Whether it's a hole or these notches. I've never seen this. I'm not even sure what the logic is to that, but I'm sure there is some logic to it. Of course, I see this all the time. And if it's some weird, like, you know, outside of this class, in the book, it's going to be one of these 3, end of story, right? But in the real world, we can get different kinds of reductions. Like we can get a system that is wide, that's going to go to something kind of narrow, and then it just kind of tapers down, right? If this is a radius, then you can use it and figure it out. It just skyrockets your R to D ratio, right? Because R goes huge.
But
And
when you have to calculate it at essentially.
not really, no, because if this is one radius, you just calculate it using that radius. Yeah. All right. That is stress concentrations. The graph's fun to read, so be careful with reading the graph. And then the R to D ratios, just be careful with that. Radius is pretty simple. And the other ones have 2, right? But you don't multiply 2 times the radius. It's just the radius, right? And then the D distance is this leftover material. That's D, and this is D. So don't complicate D. All right, you have a couple homeworks. It is 46 and 47.
On chapter 11.
Yep, still in chapter 11, cruising right along. There's a quiz tomorrow. It'll be online. If you need to look at the book, it's here. I say my coffee cup's gonna be there.
So if there's like a stress relief on something,